Welcome AP, Chapter 17, Part 2 of Acid-Base Equilibrium. This year I decided to change my order of how I did the units of AP, and I hadn't done this in over 10 years changing. But because of last year with COVID, AP cut topics that we already covered and kept topics that we didn't. And I did not want to get in that position again this year and kind of be like screwed and hurried up and learn those topics that they decided to keep. So I revamped my order and it's worked out really well. I usually would have done Chapter 17 at the beginning of second semester, but because we covered topics like Chapters 6, 7, 8, 9, I usually don't do those till third quarter, but we did those back in second quarter. So you'll see what I mean by changing some stuff. Equilibrium is like a ton, ladies and gentlemen. It is the #1 chapter. You saw it in kinetics. You saw it in equilibrium. You saw it in Chapter 16 we just did before spring break, acids and bases. And then we got the two other B's coming. We got thermodynamics, okay, thermochemistry. So since we just went on spring break because our minds were definitely going a little brain dead from, we all needed a vacation, and you know it and I know it. So I think we need a little review from Chapter 16. Okay, that's why I kept this in here, because like I said, I usually do this right at the beginning of second semester, right when we had Christmas break, but it's okay, we're going to do it now. Refreshing. According to Arrhenius's definition, and it helps if I see, it's been a while even since I've lectured. So Arrhenius's equation: an acid increases hydrogen and a base increases OH. That's why when you have a balanced equation like strong acid, HCl, I'm going to produce that H and I'm going to produce that Cl. According to Arrhenius, I need to be producing H ions. And if it was a base like sodium hydroxide, I need to be producing some hydroxide. So that concentration has to be increasing. We are definitely more familiar with Mr. Bronsted-Lowry after all the practice that we got. Bronsted-Lowry system, that an acid donates that proton and the base accepts that proton. And remember, we call this a proton, not hydrogen. Okay, he doesn't donate a hydrogen, he donates that one single proton. I always keep Lewis and acid and bases in my notes because who knows when AP is going to bring it back, but they are not bringing it back yet, so it is definitely not covered. So you can put a nice line through those ones. We talked about in Chapter 16, the stronger the acid is, the weaker the conjugate base is. So if you started with a strong acid like Mr. HCl, its conjugate base, that acid's going to donate that proton, and you're going to get that Cl minus. We talked about the strength and weakness of it, and this would be considered a negligible base. So beyond weak that we can't even measure it. Okay, so if you start with a strong acid, you will create a conjugate base that is negligible. What if you start with a weak acid, like Mr. Acetic acid, and when he becomes that conjugate, it will be a weak base, but we don't know which one's stronger or weaker, the original acid or the conjugate. So when it comes to something like this, who is stronger, we need to look at Ka values versus Kb values. Which K value is higher, and that will be the one that's more dominant. But if you start with like a negligible acid and then went to its conjugate base, I'm trying to think of a base, let's see, I went a little brain dead right here. Let's say if it was like maybe water, just say water. Water, and it donates that hydrogen, and you will get that conjugate base, hydroxide. And with that hydroxide, you will get a strong base. So if it starts with a negligible acid, you will create a strong base. When you have your neutral solution, we visited Mr. KW. If that solution is neutral, you will have not only the H and the OH equal each other, but it actually equals a value. So KW is what we call the water, the auto ionization of water. And one question I asked on chapter 16 test, and I was really curious to see what you guys would have put, and it gave you a question about, according to all the facts, which of the facts about KW is false. And the one question about, I can't remember all the choices, but KW, if it actually has a K, that should tell you something, ladies and gentlemen, about the strength of it. If it has a K, we know it's any species that is weak. Okay? Because strong acids don't have they don't have Kas, and strong bases don't have Kbs. Only weak substances, because they don't dissociate completely. So with water being Kw times that H and OH, it tells you that there must be some weak properties of water. So that's why it has a KW. I'll have to remember that question because it definitely was a little surprising on some of you guys' choices. That KW is definitely dependent on that temperature, 1.0 to the -14, as long as that temperature is 25 degrees Celsius. Okay, so that same question even gave you a choice. The KW will always be 1.0 to the -14 regardless of temperature, and you knew that definitely was false. But if you have a neutral solution, these two values would equal each other, and you would get 1.0 times 10 to the -7 molarity. Because if you take the same number, times it by that same number, you will get to the -14. If you have more hydroxide than hydronium, you will have a basic solution. And if you actually have more hydronium than hydroxide, you'll have an acidic solution. And we brought in pH that went with this. So the pH would obviously be less than 7. And if you have more hydroxide, your pH would be greater than 7. Okay? We know those scales from right there, from 0 to 14. Usually the closer it is to 0, it's a strong acid, or if it's closer to 14, it's a strong base. I only usually focus on the pH scale. I don't like to bring pOH scale into it, but just a little reminder, the pOH scale is opposite. So what a pH, oops, I can't even spell. Well, you know what I mean, opposite. Woo, we're all in spring break brain right now. The pOH scale is the opposite ranges. So for an acid, the pH from 0 to 7, if it says acidic on the pH scale, it'd be basic on the pOH scale. Strong acids, 100% completely dissociate, okay, and it does help to know who those 7 strong acids are. We use that one single arrow to dissociate it. How you write the equation, whether you want to put water in it or not, doesn't matter to me. But when you do put the water in, make sure equation is balanced. You would be very shocked at how many students on AP Test throw water in there, but then they put H+. It's like, excuse me, did you not remember to balance your oxygens? Okay, so please make sure. I'm more preferable to the second way instead of the first way, but regardless, you can do either one. Okay, acids are always aqueous. These two are definitely interchangeable. You can write either one. Same thing with strong bases. We do have 8 strong bases out there in the world. Group 1 definitely, and the heavier ones from group 2, so the heavier metals, definitely completely dissociate, one arrow, and so forth. Okay, but it's when we got to the weak acids and bases, that's when we needed to add water into it. So not only weak acids, but I can even say and weak bases. This is only for the weak bases. Then this is when you want to add water to the balanced equation. So with weak acids and bases, they partially dissociate, okay, and this is where Mr. Ice came into it. So because of that partial dissociation, we have to figure out how much does it actually dissociate. With acids, I don't tend to put water into it, but you can, but definitely with the base equation, because usually with that base and hydroxide and water, obviously the base is going to get one of those hydrogens. Actually, let me just use the example of ammonia, because you're going to see that guy pop up a ton. So ammonia, aqueous, liquid water, and Arrhenius said it, if you're going to have a base, you need to be producing hydroxide. So if you don't add the water, where is the hydroxide? Same thing with the acid. If Arrhenius says you have an acid that breaks apart, you got to be producing some hydronium. We can write a Ka expression, products of the reactants, okay, so either with the H or the hydronium, but no water, ever, ever, ever. And obviously Ka is the acid dissociation constant, is because you would only have K values for weak acids only, okay, not strong acids, because strong acids completely dissociate. We don't write water in the Ka because it's pure liquid, the concentration stays constant. So when we get to ice, ladies and gentlemen, if you do put water in it, you would just literally just kind of put an X like that in the ice chart, okay? The larger the Ka, the stronger the acid. So usually when we do that value times 10 to the negative something, if that negative something was like -1 or 2 or 3 or 4, it's kind of like a stronger weak acid, but it's still stronger. It's when you get those exponents like -9, 10, 11, 12, 19, whatever, that's so beyond weak. So the higher the K value is, the stronger the acid. If your Ka is greater than 1, then that means that the acid completely dissociate, and that's why it's a strong acid. And strong acids have no Ka values because the K values are greater than 1. They completely dissociate, so they don't have a value besides just greater than 1. When we did our ice, there was a way that we could make an assumption about X. So that way we can get rid of one of the X's in our equation. So to see how large it compared to the initial concentration, so we're basically trying to figure out if the acid or base, how much did it actually dissociate? Okay, and we know these percentages are very low. Okay, if that X, that assumption that you say about X, if it's less than 5%, that's a good assumption. Okay, so it's all about that number 5%. But if it's greater than 5%, this is where the quadratic equation would have come in. We're not doing the quadratic on the AP test this year. Okay, so we're not going to worry about that. So assume galore. You would then have to check your assumption. Okay, so it's called percent ionization. You take the H at equilibrium according to your ice chart, and your HA, whoever that initial acid was, times 100, and we're looking for that less than 5%. Okay, so the greater the percentage, greater percent, the more it dissociates. Okay, and that's why strong acids are 100% dissociates. If it was for a base, so this is obviously for an acid, for a base, you would have hydroxide, hydroxide at equilibrium, and then you would have your base, initial, times 100. Okay? The higher the percentage, like I said, the stronger the acid, and strong acids would 100% completely dissociate. So you're going to see my notes, ladies and gentlemen, do not look like the usual Rodriguez 50-page novel. Is because this summer I got to do most of them, but there's about 4 chapters I did not get to finish revamping with all these cool practice problems that College Board released back in the spring. So you're not going to see a lot of examples in my notes, but you will see the notes part. So with these examples, I'm going to be relying on a lot on those AP Daily videos. Okay, so these AP Daily videos, you're going to get the majority of your examples from them. Okay, I'm just going to give you the notes part. You know, in practice, in class, we will practice to death. But these AP videos are going to be all the ones from 8.4 to 8.10. For a small chapter, there's so many videos, okay? Or I'm sorry, so many learning targets, 8.4 to 8.10, plus that when we get to the end, 7.11 to 7.14. We got a new K coming in, the very last K, thank goodness, called KSP. So we saw the videos for chapter 7, but we stopped at 7.10 because we hadn't got to chapter 17 yet. So see all those learning objectives? You got 6 different learning objectives up there, plus another 4 down here. And that's not even talking about the A, B, C, Ds on those learning objectives. For a little chapter, it's very massive in points on the AP test. So we got to rock this. First topic I'm going to start with is something called common ion effect. I ain't going to lie to you, ladies and gentlemen. This is where students stumble. It's right in the very beginning. These 2 very first videos are where students stumble. The common ion effect is basically what it's talking about. You need to have a common ion that's part of that equation. So when you dissociate, a weak electrolyte is decreased by the addition of a strong electrolyte that has a common ion with that weak electrolyte. So what the heck did Rodriguez just say? So when you dissociate a weak electrolyte, whether it be a weak acid or weak base, and that dissociation is decreased, okay, you actually made it even more weaker, okay, so that dissociation is decreased, okay, by the addition of a strong electrolyte. So that strong electrolyte could be maybe some strong acid, could be a strong base, heck, it could even be a salt. Okay, because remember salts, aka ionic compounds, strong electrolytes. But you have to have a common ion with that weak electrolyte. Okay, so say for example, the ionization of weak acid. So here's Mr. Weak Acid, and this is my equation. So if I wanted to bring in an additional chemical, maybe acetate, by adding a strong electrolyte, like Mr. Sodium acetate, aka ionic compound. And what will happen is you will get a shift. Okay, so remember, this is called applying a stress. Hopefully this is sounding familiar from the end of chapter 15. Mr. Le Chatelier is back. By adding that salt, where are you affecting the equation? I'm affecting here. Now, but I just said I'm adding some sodium acetate. Where's the sodium? What happens is when this guy hits the water, it will completely dissociate. So you'll get your Na, and this guy hits water, and I'm going to get my Na plus, and I'll get my acetate. Okay? So in my solution, I'm going to form some Na plus, but I'm also going to form some more acetate. So what does this look like in like the beaker? Because you really need to visualize this so that way you understand. So in here, in my beaker, in the beginning, okay, originally, we'll do this in one color. So originally I have my H plus, I got my acetates in here, but because acetic acid is a weak acid, I even have the acid, original acid sitting in here because it's a weak acid. So aka weak acid doesn't completely dissociate. But then now, here comes the new part. What if I add sodium acetate to this, aka a ionic compound, a salt, and I have something called a common ion effect. And I'm just abbreviating that because of time. Don't do that on the AP test. When this guy hits water, he's going to associate 100% dissociation. But the question is, which of these 3 chemicals will he affect the most? So when this guy hits water, I'm going to be producing some sodium, and I'm going to be producing some more acetate. I'm going to be producing more of him. So the concentration of that acetate will increase. But you're adding more acetate and more acetate and more acetate. What's going to happen to him? What's going to happen to hydroxide? What's going to happen to this acid? Well, remember Le Chatelier's principle. If, here's my equation, the original acid and C2H3O2. And if I add more of him from sodium acetate, we don't care about the sodium. Sodium's not part of the show. We care about this acetate because that is our common ion. And what's going to happen to our equation? It's going to be a little teeter-totter going on. It's going to be looking like this. So, your favorite explanation ever. So, to re-achieve or reestablish, either one that you want, the reaction must shift to the left. Okay, we need this guy to shift over here so we can get it back to equilibrium. But how are you going to get it to shift to the left? By decreasing some H and increasing some acid. Okay, so to reestablish equilibrium, I have to decrease some of that H+. What will happen to pH? That's a good question. So if my hydroxide is decreasing, I'm losing more hydroxide, So what also is happening? Your pH will change. And we have an equation that will help us figure out that pH change. So you're going to be decreasing some hydroxide, which means your pH will definitely be getting higher because you're not making it more acidic. You're making it less acidic. So that pH changes because it's going to be less acidic. So that pH will eventually, it will increase because I have to add, I have to lose some hydroxide and add some more weak acid to it. So it's going to be less acidic. Le Chatelet, ladies and gentlemen, is back. So what's the rest of my story? Because we're not going to put that period there. Decrease some H, increase some acid, so that Q equals K. All right, you get no love, ladies and gentlemen, from AP without mentioning that Q and K. So this stress, ladies and gentlemen, this is where Q comes in. Okay, so this causes a reduction of H+, and it's going to decrease the percent ionization of this acid. Okay, because remember, with percent ionization, you're taking that H+ at equilibrium, but we just said he's going to be decreasing. And if he's decreasing over that original acid, that percent is going to get less and less and less. Okay, so if you look at it as a math standpoint, I think you can probably see where we're going. By adding the sodium acetate, we have disturbed the acetic acid at equilibrium. So in effect, we have added a product of this equilibrium, and this is called common ion effect. Ladies and gentlemen, I can't just add any old salt. I can't just add anybody. It has to be a common ion with either the weak acid or the weak base. With the weak acid or the weak base. It has to have somebody in common with that. So if I would have had like another weak acid, so like maybe like HClO is a weak acid, and when this guy hits water, I'll get my H+ and my ClO-. If I wanted to add a salt to this, then I would just have to pick a salt that is not only ionic and has a common ion with him. Okay, so like somebody like maybe like sodium hypochlorite or potassium hypochlorite, or if I want to pick a different metal, magnesium hypochlorite 2, and obviously that 2 chloride, I'm even going to produce more of that common ion effect. So the extent of the ionization of this weak acid is decreased by adding to the solution a strong electrolyte that has an ion in common with this weak acid. That's where we're headed, ladies and gentlemen. The math is no different, except now, instead of starting with one thing that you know and no products, you're actually going to be starting with a reactant and a product. There's only one change to the